Hello mathematicians. Our last example of resisted motion is when we have a particle moving upwards in the resisting medium and it's under the influence of gravity. So in that case our overall force is the result of two separate forces, the downward pull of gravity and the resistive force, which while the particle is going upward also points down. So this is the case when objects are projected vertically in a gravitational field. The resistance force always acts against the motion. So if we got to the point where the particle was travelling down, then that resistance vector would now point upwards. We also need to remember that when we're travelling vertically, that the highest point is the point where the velocity equals 0. And also that the motion is symmetrical in terms of time. So if we look at our first example, a particle of unit mass, so mass of 1 kilogram, thrown vertically upward with an initial velocity u, we've got a resistance mkv, and we have to find the greatest height reached and the corresponding time. So, as always, setting up our picture is key. So we're starting at ground level with displacement 0, time 0 and initial velocity u. Sometime later we can put that one in, and right at the top of the flight we'll have displacement equals h and final velocity equals u. Our two forces acting are gravity downwards and the resistance mkv. So we set up our equation, mx double dot equals that. The m cancels out, as we can see, and because we want things as a function of distance, we'll use v dv dx. So v dv dx equals that. We gather together the v's to one side, so we've got the integral from u to 0, because we're going to the very top, and that equals the integral from dx from 0 to h, and we know that that just simplifies to h. So we have this integral v over g plus kv. It's not a log, it's not a partial fraction straight off, so when all else fails we try to do the long division and see if we can make it simpler, and it works in this case. So if I divide v by g plus kv, it's slightly tricky in that we have 1 on k up the top, but our integral from u to 0 of v over g plus kv becomes these two separate integrals, minus 1 on k, which will be easy for us, and this one, which will also be easy for us because we can take the g on k out the front and it will become a log problem. So we set up our integral ready to turn into a log. We do the integral, put the limits in, and we get to this spot. We use our log rule to write that, and then algebra to write this, and we have the expression for the maximum height. Now, because our expression for maximum height didn't have t in it, and we want the time to maximum height, we go through the process again. So we now want to get our equation in terms of time, to get the time for maximum height. So starting from our force equation, simplifying as before, the version of a that we use this time is dv dt. So again, gather all the v's to one side, all the t's to the other, and put in our limits of integration. We can see that the right hand side just becomes t, so we're integrating minus this, which will become a log integral. We apply our log rule. We take the negative out through the brackets, and we finally get our expression for t, and then just simplify what's in the brackets. In our second example, we have a resistance mkv again. It's projected upwards with an initial velocity u equals g on k, and we have to essentially find the equation for velocity and displacement in terms of, as we can see, time. We also need to find the greatest height reached. So, our initial picture, our two forces acting downwards are these, our initial conditions down here, and sometime later they will be displacement time and velocity values. So we set up our original equation, we notice that the m cancels out, and then because we want v as a function of t, our a will be dv dt. So we drag the integrals dv, all the v's to one side, the t's to the other, as we've seen, and we get this. So the right-hand side becomes t, and our left-hand side is the integral, is an integral which will yield a log. Replace u with j on k, and when we do our substitution of limits, we get this. Our log rule will give us this. Then, because we know that we're after an expression with t as the subject, we will take the k across to the other side so that we can undo the log by allowing us to take the exponential of both sides, rearrange, and then keep rearranging, so that we can make v the subject of the equation. Now, we also want x as a function of time, so we can use the fact that v is dx dt. So we will integrate dx dt with separating the x's and our expression for t over here. So the left-hand side simply becomes x. We're going from 0 up to x. The right-hand side, we're going from 0 up to t. So we substitute in our limits, do the algebra, and we get our expression for displacement as a function of time. We then recall that the greatest height occurs when v equals 0. So from equation 1, which was v as a function of t, we get when v equals 0, so when is an implication that we're talking about time. So that was when 2e to the minus kt equaled 1, so t equaled this. And we plug that into our second equation, which was displacement as a function of time. We go through the algebra, be careful with the logs, and this is then our expression for mass. Okay, so for our next example, we have a particle of unit mass, so mass 1 kilogram, thrown up with velocity u. We've got a resistance kv squared per unit mass, and we have to find the greatest height achieved by the particle and the corresponding time. So when we set up our picture, here's the particle being thrown up into the air. The force of gravity is going to act on it, and it's got its resistance of kv squared per unit mass. The initial conditions were as shown. These are the conditions later on, and I suppose what we could have done also is put in an x equals h and taken it from there. But let's continue. So we know this bit, greatest height is when v equals 0. Somehow or other we're going to get, we'll need velocity as a function of time and displacement as a function of time. So set up our initial dynamic equation, if you like, that mx double dot is minus mg minus mkv squared. Do our division through by m, and we want x double dot to be in the form dv on t, because we want to get it as a function of time. So we're going to go that gathering together the v's to one side, we've got the integral dv over g plus kv squared. and our minus out here, which is going to enable us to switch the limits of integration down here. On the right hand side we've got the integral dt, which will of course just become t. So with our limits switched, we're integrating this, which we recognise as, well, we go through our alternatives, it's not a log. We recognise it as a standard integral of tan to the minus 1, but we've got to just do a little bit of refinement on it at the moment. So to get the v squared by itself, we'll divide through by k on the bottom and shift it out the front here to counteract it. So we've got this integral. And then when we go to our table of standard integrals, we've got 1 on square root of g over k, so that gives us this bit. Our 1 on k is still sitting out here. Tan to the minus 1, v on square root of g on k, and with these limits. So finally we get to t equals this expression here. Now to get the equation for maximum height, then we now want to link v and x, so we're going to use this form of the acceleration. So v dv dx is this. We rearrange our integral, so bring all the v stuff onto this side, and we've got this, and that equals the integral dx from 0 to h, which of course becomes h. Now on the left hand side we can again use that negative to change the limits around, and we would like to have 2kv on top of this, so that will give us 1 on 2k out the front, so that we can then integrate that into a log. We can then plug our limits in and do a little bit of algebra on what's in the brackets there, and we've got our expression for maximum height. Now our last example here, sorry to the non-physicists, but it does bring in a few physics concepts. We're told acceleration due to gravity outside Earth is inversely proportional to the square of the distance from the centre of the Earth. So the key thing about that is that it means that A is k on x squared, and it's directed down towards the centre of the Earth. So in the first part, neglecting air resistance, show that if a particle is projected vertically upward with an initial velocity u from a point on the surface of the Earth, so not the centre of the Earth, its velocity in any position x is given by this expression, where r is the radius of the Earth and g is the acceleration due to gravity. So our diagram here is vital. So here we have the pathway, if you like, going from the centre of the Earth out to some point. So the value of x is measured from the centre of the Earth. I've already mentioned that the dynamic equation is mx double dot equals mk on x squared, so the m's will cancel. At the Earth's surface, which is where the rocket ship will be launched from, a particle, sorry, then the value of x is already r, t will equal 0, and v is u, the launch velocity. At some later time, any later time, we've got that, and at maximum height, we have that the value of x is h and that v equals 0. So, start from, as always, our dynamic equation, and because we want essentially velocity as a function of displacement, then we'll set up our equation so that we use this as our expression for A. So we've got this part here, and then we'll gather the v's to one side, the x's to the other, and put in our limits. So we've got this bit here. I haven't put v equals 0 just yet. I've just been working with v, and I'm going from r up to some height. So I'm getting a general equation first. And the reason for that is that no particular reason. I'm going to evaluate k later on. I could have done it elsewise. So I do my integral here, so v squared on 2 from the initial to some final velocity. This just a standard 1 over x from there to there. Plug in my limits, multiply through by 2. Then account for these negatives here by rearranging what's in the brackets. Shift the u squared over to the other side, and I get an equation for the velocity at any height as a function of the initial velocity and the displacement. Now, I need to know something about k before I can get the expression up above. So when x equals r, when we're at the surface of the Earth, then the acceleration due to gravity, which is k on x squared, becomes k on r squared, which is minus g. So k equals minus g on r squared. So we simply plug that into our equation and we get the expression that they wanted us to, which gives us the velocity as a function of height. Then we realise that we reach the greatest height when v equals 0. So I simply, to get v equals 0, I need this side to equal 0, which will happen when u squared equals that. Just do a bit of algebra, rearranging it to make h the subject, and we get to an expression for maximum height. Now for our last part of this question, this is where the bit of physics comes in. So we've got this equation for velocity at any height, which we derived earlier on. So in terms of what escape velocity is, what we need is for v to be always positive basically, so the particle never heads back the way it was coming. So as we head towards infinity and beyond, then v always needs to be positive. And I guess when we actually get to infinity, that's when the particle will stop travelling away. So essentially, it boils down to finding when v equals 0. So v will equal 0 when this happens, but it's a little bit more, which is now that we want x to be at infinity. So that means that this term disappears, u squared then becomes 2gr. When we actually plug the numbers in for the radius of the Earth, we get 11,200 metres per second, or 11.2 kilometres per second, which is, as the physicist might recognise, the escape velocity for Earth. Maximum height.